Today I'm going to be talking about bio-inspired flights. And really the question I want to ask is, what can we learn from biological flyers, the birds and the bees of the title, that can help us to build more efficient, more effective aircraft, as well as to develop new air capabilities? Flight has evolved, been invented, been discovered, ideas have been borrowed or stolen several times on Earth, many times on Earth. And here, of course, I'm thinking about insects, pterosaurs, the flying dinosaurs, birds, bats, and as well I would classify fish and marine mammals in this category as well, because the motions of their fins is actually very similar to the motion of birds' wings through the air. And, of course, the latest example is man's use of flight concepts to create aircraft. Man has long been fascinated by the possibilities offered by flight. And this, in fact, goes back at least as far as to Leonardo da Vinci, who in the 1480s spent a lot of time developing concepts for flight vehicles and documenting them in his notebooks. And here I'm just showing a couple of examples. There's on the right, an example of a rotary winged aircraft designed to have a person sit in the cage beneath a sort of a sail wing structure and turn a crank to produce the turning motion of that sail to hopefully achieve liftoff. Leonardo da Vinci also spent a lot of time examining studying the flight of birds, so looking at flapping flight, and only later in life started looking at soaring flight, which probably would have been the more profitable route. Nonetheless, he designed a number of flight vehicles, an example of which is shown here on the left, in which a person was expected to lie on a plank of wood and use the arms and legs to create the flapping motion of those wings, much like a bird. Now, none of these, as far as we know, were actually built or tested. And in fact, most of them are completely impractical. A person just doesn't have the power to be able to flap a set of wooden wings and support his own weight. But Da Vinci remained fascinated with flight throughout his life, and I think that's encapsulated by the quote that I have here. Once you have tasted flight, you will forever walk the earth with your eyes turned skyward, for there you have been, and there you will always long to return. Of course, Leonardo da Vinci never flew, and like Leonardo da Vinci, I'm interested in flight, but I don't have to actually fly. I am interested in specifically small unmanned aircraft that are so small they couldn't carry a human on board. And here I'm talking about aircraft with no more than 3 to 4 meters wingspan. So the question is, what can we learn from biological flyers? And here I've just got a sampling to remind you of sort of the diversity, the different modes of flight, the different sizes and shapes of the various flyers. And really what I'm trying to get across is that there are some things that we can take from biological systems and transfer into mechanical systems that can be quite useful. Now, the first way that we can look at this, for all that they seem very different, there are some underlying principles here. The first way we'll look at this is just with geometrical scaling. So if every, what I've actually plotted here is data for a large number of insects, in fact about 1,000 different insects from 12 different insect families. This is just data that's available in the public literature, and I've plotted the wingspan for each individual insect as a function of its mass. Now, if geometrical scaling held perfectly for all of these different insects, we would expect them to cluster along a straight line, like the line that I've drawn there. We know, of course, that what's represented here is everything from cockroaches to butterflies to grasshoppers to dragonflies. They are not geometrically similar, and yet they sort of follow roughly this relationship. If we looked individually at the families, they're much closer to following this sort of straight line relationship, which says that the length dimension should be proportional to the cube root of the mass, just the geometrical scaling law. Now, I'll add on to that plot, I'll add birds and bats to have a look at those. And what you see is that they fall very much along that same line. They cluster along the same line. In fact, the clustering is tighter because if we think about birds, they are rather more geometrically similar than the various insects that I mentioned, and bats as well. And then if I put on flapping winged aircraft, you'll see that they also fall along that line. Now, I'll also add fixed-wing manned aircraft. And what's surprising to me is that if we've extended that line all the way up to the size and the mass of manned aircraft, we actually find that they reasonably well sit on that line too. And I'll add fixed-wing unmanned aircraft. You see quite a bit more scatter around the line, but basically it falls along that same line. And some of the differences that you're seeing they're due to the fact that there's a large diversity in the designs of unmanned aircraft. And we also see a cluster here at the top of some very different designs, and I'll give you a little feeling for why that is in just a moment. But finally, I'll add rotary winged aircraft, and I haven't distinguished between manned and unmanned, but I think you'd understand that at about 100 kilograms, there's a possibility of things above that point being manned, but below that point, that's less than the weight of a human pilot, so it's necessarily unmanned. And what we find is there's a lot of diversity there as well, and that in general, rotary wing aircraft tend to be more compact than their fixed wing counterparts for the same mass. Nonetheless, they're following that same trend again. And just to remind you of what we're talking about, we've got insects as tiny as Incarcia formosa with a maximum dimension of no more than 1 millimeter, through to dragonflies. Interesting new vehicles that have been developed, such as Dynamics Black Hornet, that's recently been purchased and deployed by the UK for their army. Hummingbirds, which actually have a similar mass and scale to the Dynamics helicopter. Things like flying foxes. This is the largest specimen on Earth, or species on Earth, the Malayan flying fox. And typical small manned portable aircraft like AeroVironment's Puma, which has a wingspan of 2.8 meters. And then the more exotic designs of unmanned vehicles. This is a design that was tested by NASA. It's called Helios. It was designed to serve as a pseudo-satellite in the stratosphere. So it's got quite a different form factor to what we would normally think of for manned aircraft. And that's why you see this clustering. These would all be vehicles similar to Helios. They're designed for high-altitude, long-endurance missions, spending months or maybe years as pseudo-satellites in the stratosphere. And then finally, at the top of the plot are things like jumbo jets. And in fact, the very top point there is the A380. So I think you can see some of the differences, but you can also see the overriding similarity. And this is valid over 14 orders of magnitude of mass. There's very little that we can think of that's a given law or an equation that describes something that extends over 14 orders of magnitude. And in fact, if we look at that actual line that I've drawn, if we have the length scale in units of meters and the mass in units of kilograms, the equation that describes that line is that the length scale is equal to the cube root of the mass. And I think this plot also points out where the various modes of flight are applicable. Flapping flight being at the low scale, up to masses of about 1 kilogram. Fixed wing flight being at the very largest scales and going down approximately to around the median bird or bat. And rotary wings spanning from the low end of the fixed wing manned aircraft, down into the regime of insects. So I think those are sort of the interesting places to work as well. So what have we done in this area? How is it that we're hoping to get inspiration from nature to design better or unique aircraft? We have been thinking about building flying robots. We want to be inspired by nature, but we will not be trying to mimic nature. That would be impossible, number one. And secondly, biological species have evolved under a given set of constraints that may be completely different to the set of constraints that are relevant for a mechanical system. And those are the mission constraints and the sort of materials that we have available. And we also have other mechanisms than natural systems have. We have rotating machinery, for example. So while we can be inspired and learn from nature, we won't try to mimic it. One of the things that we've done is to look at the aerodynamics of flapping flight in one of our research programs. And we've also looked at some of the features of flapping wing flyers, including their wing corrugations, wing flexibility, and concepts like tandem wings, such as you'd think of a dragonfly. So I'll show you an example of some of the work that's been done here at DSTO. This is a tandem wing flapping device that's built around 2 commercially purchased ornithopters, or bird-like flappers. It's been tested in our low-speed wind tunnel here at Fisherman's Bend, and I'll just trigger the video. You'll see the wings start out flapping in phase with each other, and then they'll go out of phase. They'll be flapping with a 180-degree phase differential. And what we were trying to study with this, of course, in the wind tunnel, there's a steady oncoming flow of air. What we're trying to study is the interaction between the wake that's shed by the forewing pair with the hind wing. And what we want to do is examine whether or not we could actually get control of that vehicle so that we would be able to hover in that steady cross flow of air. What we found is that for a phase differential of around 180 degrees, probably more like 200, we could actually get a very low net thrust, so very small speeds in the horizontal direction, and all of the forces were in the vertical direction, lift. And that would mean that we would be able to hover that vehicle in that steady cross flow of air. So that's interesting from the point of view of what we might develop as a prototype for a vehicle, because it suggests that we could use a simple mechanism like adjusting the phasing to achieve hovering, to transition from steady forward flight into hovering. And I think what it also points out is that there's a level of embedded intelligence that will need to go into that sort of system. We won't be able to predict ahead of time what it will take, what wing motions would be useful to be able to turn left or turn right, or to resist gusts or travel at a certain speed in a given crosswind. We will need to develop a system that is adaptive and that has feedback control and essentially will teach itself to fly. And one of the other things that this suggests, and that in fact is something we see in nature as well with dragonflies, is damage tolerance. This dragonfly has lost a significant portion of one of its hind wings, and yet it's still able to fly. So taking a lesson from that, we know that if we can develop an adaptive control system to actually allow the vehicle to teach itself to fly, we think that it might be able to be damage tolerant as well, which could be quite useful. If you have a small flapping wing device that's designed perhaps to fly through a city, enter an open window or door, say it clips the door frame as it enters the building, it might lose a portion of one of its wings. If it has adaptive control on board and this embedded intelligence, it should be able to learn how to fly again and complete its mission. Before I move to that, let me just mention another concept that we get from insects that's, well, it's quite useful, and that is taking advantage of resonance systems. That's something that's used by insects and, in fact, hummingbirds. And I've got a really simple illustration here of a very simple system with a natural frequency, and can kind of give us a view into how to use a resonance system to get power efficiency on this sort of device. A pendulum or a swing, in essence, has a natural frequency at which it wants to oscillate. We know that if we put forcing into the system at the same frequency as the natural frequency of the system, we can make the child swing higher and higher. We can take advantage of the fact that the pendulum is transferring potential energy into kinetic energy, and if we force it correctly, we can amplify that motion. Now, the same is true for insects. In fact, insects have a material called resilient in their abdomens, and they have a wing structure, the mechanics of which are set up to be sort of spring-loaded. And what happens during the motion of their wings is that energy is stored elastically in the resilin in their abdomens and is then expended on the counterstroke. So they're only needing to put in a fraction of the total amount of power to drive their wings. They're able to, for example, bumblebees only put in 5% on every wing stroke. They put in an additional 5% of power. So it's quite a bit more efficient. Another aspect that we can take advantage of and we can learn from nature is in fixed-wing flight. This is a flock of white storks. They're circling with their wings outstretched in a rising column of warm air. They're soaring a thermal updraft. And we can do that with aircraft as well. Here's an example. This is a flight trial we performed a couple of years ago using an aircraft called Kahu with a 1.8 meter wingspan this was done in collaboration with our TTCP partners in New Zealand. And here, this is just a snapshot from the ground control station playing back this soaring experiment that we performed. So you see wind vectors. It was quite a howly day in New Zealand, unsurprisingly, with 16-knot winds. The operators were flying the aircraft, hunting for thermals. They flew from here. This is the beginning of the flight path that's shown in pink. They flew across what they thought was a thermal updraft, turned the aircraft around, and then went into soaring control. So from this point onward in this flight path, the aircraft is completely autonomously controlled. The onboard algorithm actually can predict where the center of a thermal updraft is and take into account the wind, because what happens with thermal updrafts is they're not just neat columns of air, they're actually blown with the wind. So what you're seeing is this aircraft circling and following that updraft downwind. And that was quite successful. That flight was performed with the motor turned off. So in essence, the aircraft is flying for free, and it gained about 500 meters of altitude during that portion of the flight. There are other concepts as well, things like swarming that might be of interest for autonomous control of aircraft. Swarming is often thought of, and in fact this is a picture of auklets in Alaska, birds in a very large flock, probably thousands of individuals. And the collective behavior that you're seeing is a model for the sort of cooperative and collective behavior that we might want to utilize for the control of multiple unmanned aircraft. In essence, each auklet, each bird is an individual acting of its own accord. It's responding to its nearest neighbors, say the 6 or 8 closest birds to it. It's responding as rapidly as it can to their behavior. And what you end up with is this overall coherent behavior that you might not expect from those thousands of individuals. So I think I've summarized a couple of the activities that we've done, and I want to note that these are done under our, the 2 activities I've highlighted were performed under our strategic research initiatives in unmanned aircraft systems and also in the Signatures Materials and Energy program. And I think it's been interesting to do this sort of presentation at DSTO. It's not the usual kind of technical presentation that we would often do. To put it in TED-Talk format, I think is a useful exercise to see if you can really boil down the essence of the message. And also the goal with a TED-Talk, of course, is to communicate with a scientifically literate audience, but not an audience of scientists. So I found that quite interesting to do. But I think what we have to remember is that this sort of far-reaching ideas and emerging technology is something that our clients are very much interested in having us do. In fact, DCAP, I think, would be expecting us to be looking into areas like this for the future. So finally, I'll just acknowledge the many people who have contributed to the research programs that I've talked about today. And I'll take any questions. I have no idea if I'm ever coming.